Okay folks, going to run over a couple of the tutorial questions on electric force and electric field strength. So this is question 6 in the tutorial question booklet. It says 4-point charges P, Q, R and S each have a charge of 4 nanocoulombs and they are situated at each of the 4 corners of a square. So they're all 4 nanocoulombs. And we've to determine the electrostatic force, the magnitude and direction of that force on charge P. So Q and R and S are all going to be repelling charge P. And we're going to need a vector diagram for this. I bet you thought we had forgotten all about vectors, but unfortunately vectors are still very important in physics. So let's take them one at a time. Points Q and P, if we work out the force between those two charges, we can use the shortcut F equals KQQ over R squared and use 9 times 10 to the 9 for the constant. And the two charges are 4 nanocoulombs, so 4 times 10 to the minus 9 times 4 times 10 to the minus 9 is 4 times 10 to the minus 9 squared. And the distance between them is 0.1 metres. And don't forget to square that distance. If you do that on your calculator, you get 1.44 times 10 to the minus 5 newtons. Now, do we need to do the same for the charge at point S? No, we don't, because it's the same charge at the same distance. So it will also be 1.44 times 10 to the minus 5 newtons, but we can't just add them. We have to add them as vectors because they're acting at right angles to each other. So if we draw a little right angled triangle here, there's my vector Q to P, and there is my vector showing me S to P. Then, if we join them up, then that hypotenuse of that triangle will be the resultant force produced by both the forces from those charges. So, it's a right angled triangle. We can use Pythagoras here, so 1.44 squared plus 1.44 squared, all square rooted, gives us a resultant of 2.04. Don't forget that's times 10 to the minus 5 newtons. Now we've still got a third one to do. We've still got the charge at position R, so R to S. And we need to go back to the start with this one because although it's the same size of charge, it's at a different distance. And we need to work out that distance first. So bear in mind it's a square and the side of the square was 0.1 metres. So if we want to do F equals KQQ over R squared, then it's still going to be 9 times 10 to the 9 for the constant. It's still going to be 4 times 10 to the minus 9 squared for Q times Q. But R this time is going to be different. We'll need to sketch a little right angled triangle here showing us the sides of the square. So the diagonal in the square will be 0.1 squared plus 0.1 squared square rooted. And that gives us a hypotenuse of 0.14 metres. So that's the distance between the diagonal and the square using Pythagoras. And so we put 0.14 squared in for the bottom line there on the right. Do all that on your calculator and that gives you a force of 0.73 times 10 to the minus 5 newtons. Now, can we just add these two together? Well, the answer is yes, we can. Because these two vectors are acting in the same direction. So the total force will be the 2.04 plus the 0.73. That gives us 2.77 times 10 to the minus 5 newtons. So the reason we could just simply add these together is because the resultant vectors are in the same direction. Now, because it's a vector, we need a direction. So if you look at my wee right angled triangle at the top there, you could say south, southwest. I suppose you would get away with southwest, but halfway between 180 degrees and 270 degrees is 225 degrees. 3-figure bearings. I know you did that in higher over a year ago, but hey ho, we're still going to need them. You might need to look over that a couple of times. That's tough. Why is it tough? Because the vectors are tough. Now there is a part B to that question as well. It says if you put another charge bang in the middle of the square, what would be the resultant force on it? Well, the resultant force would be 0, because the 4 charges at the corners of the square have all got the same charge, so the forces that they exert on it will all be the same. They'll be balanced, equal forces in opposite directions. That's one of these must justify questions, so you need to have an answer and justify your answer by stating that the forces are balanced, they are equal forces acting in opposite directions. That's pretty tough. Okay, this is question 9, and this is a tough trigonometry question. Right, we've got 3 charges. Q3 is minus 2 microcoulombs, minus 2 times 10 to the minus 6. Q1 is minus 1 microcoulombs, and Q2 is a positive charge of 3 microcoulombs. They're all written underneath the diagram, but I'm just putting them on there to make it a bit clearer for myself. So 2 negative charges and a positive charge, and we have to calculate the resultant force on Q1, and we need the direction as well. So first thing I'm going to have to do is work out what each of the forces are then. Q3 is going to repel Q1 because they're both negative, and Q2 is going to attract Q1 because they are opposite charges, and we'll bear that in mind when we do our vector diagram at the end. So let's work out those forces then. Between Q1 and Q2, if we do our Coulombs Law equation, KQ1 Q2 over R squared, we can use the shortcut of 9 times 10 to the 9 for the constant, and Q1 is 1 times 10 to the minus 6, and Q2 was 3 times 10 to the minus 6. I'm not putting in any negative signs here. And R, the distance between them, is 0.15 metres, and don't forget to square that. Now that will give us the force, and that force is 1.2 newtons, and it's going to be acting to the right because Q1 is going to be attracted to Q2, because Q1 is negative and it's attracted to Q2 that is positive. So I'm now taking my positives and negatives into consideration. If we work out the second force between Q3 and Q1, same equation, 9 times 10 to the 9. Our charges this time, Q1 is still 1 times 10 to the minus 6. Q3 is 2 times 10 to the minus 6. And the distance between them is 0.1 metres. Don't forget to square it. Gives you an answer of, it's a slightly bigger force because it's a smaller distance, is 1.8 newtons. And the direction of that force, Q3, is repelling Q1, so it's going to push Q1 down to the right, so downwards to the right, because it's being repelled. Now, we have to add these together as vectors. So let's do a little vector diagram showing the 1.2 newtons acting to the right and the 1.8 newtons acting down to the right. And we know that angle because it's given in the diagram in the question. It's 120 degrees. If we drew a little quadrilateral there, then those angles would be the same, 120. Now, this is where you might give up, because that's not a right angled triangle. And if it's not a right angled triangle, we need to use the cosine rule. If we want to find the third side of that triangle, we're going to have to use You remember the cosine rule? If we want to find that a squared is b squared plus c squared minus 2bc cos a. Substitute everything in for b and c. 1.2 squared plus 1.8 squared minus 2 times 1.2 times 1.8 times the cos of the angle. Well, that angle is 120 degrees. If you do all that in your calculator, you'll get a squared. A squared works out to be 6.84. And then if we square root that, we're going to get 2.62 newtons. Now that's the magnitude of that side of the triangle. We now need the direction as well. And for the direction, we're going to need that angle in the triangle, the first angle. Because remember, our vectors are going in that direction. So from start to finish, we need the starting angle. And for that, we're going to need the sine rule. I don't think you would ever be asked this in a final exam. There's too much trig going on, but it's a nice exercise in trigonometry. So there's your sine rule. We know what A is, we know what sine A is. We are looking for sine of angle B. And we know what B is, it's 1.8. So if you rearrange to get sine B, there it's rearranged, and B works out to be 37 degrees. Calculator in degrees, by the way. So our final resultant force is 2.6 newtons at, well, if you want it as a three-figure bearing, 127, because it's 37 degrees plus your 90 from north, or 37 degrees as shown in the diagram. Tough because of the vectors. I think that's too tough for a past paper. So let's look at past papers and let's look at 2, just to see the standard that you would meet in an exam and the standard you'd probably meet in a prelim or a secure assessment. So part A, what's meant by electric field strength, that's a definition. Remember, you should always write your definitions down in words. So it's the force per unit positive charge at a point in an electric field. Don't forget, it's always a positive charge that's referred to in the definitions for electric fields. Right, part B, 2 identical spheres, each with a charge of 22 nanocoulombs, are suspended from a point P by 2 equal lengths of thread, and they repel and come to rest. So if they have come to rest, the forces are balanced. So those 2 charges are at rest and they are repelling each other. We know the weight of each sphere. Weight acts downwards, 9.8 times 10 to the minus 4. And the question says, by considering the forces acting on one of the spheres, show that the electric force between the charges is 5.66 times 10 to the minus 4 newtons. It's a show question. So let's just think about one of these charges here. We'll draw a right-angled triangle. The vertical component of the tension in the thread has got to balance the weight of the thing. And the horizontal component will be the electric repulsive force. So we know the weight is 9.8 times 10 to the minus 4 newtons. And we know the angle's 30 degrees. So if we do a little bit of trigonometry here, the tan of that angle, tan 30, will be the opposite over the adjacent, and it's the opposite side we're looking for. So tan 30 will be equal to the electric force divided by the weight of one of the spheres. If we rearrange that to get Fe, it's going to be 9.8 times 10 to the minus 4 times the tan of 30, and hey ho, there we go. We get 5.66 times 10 to the minus 4 newtons. It's a show question. That's what we have to show. That's what we've found. Now, why do they give you show questions? It's so that you can use that number in the next part of the question. So we're then told, by considering that electric force, calculate the distance between the centres of the spheres. So we're back to our Coulombs Law equation. We can use the shortcut F equals K Q1 Q2 over R squared, and it's R squared that we're looking for. Well, it's really R that we're looking for, the distance between the centre of the charges. So R squared is going to be equal to, let's just substitute our numbers in, so we can use the shortcut. K is 9 times 10 to the 9. The two charges are both the same, so it's 22 times 10 to the minus 9 squared, because they're multiplied by each other, and we divide that by our electric force that we were told, 5.66 times 10 to the minus 4. Pop that into your calculator, don't forget to square root it, and you get an answer of 0.088 metres. 8.8 centimetres. Remember, it has to be realistic. So if you get some crazy number, go back and check your calculator. Right. This is another paper, 2017 paper. Oh, notice something similar. Exact same question to start off with. Different year. What's meant by electric field strength? It's the force per unit positive charge at a point in an electric field. Don't forget to mention it's a positive charge. Then part B of the question, it's looking like vectors again. We have A, B, C and D are the corners of a square, and two 4 nanocoulomb charges are placed at B and D as shown in the diagram. It's a show question. We must start off with the equation from the relationship sheet then. We have to show that the electric field strength at point A is equal to that number. So we take our electric field strength relationship. Remember, you can lift it straight from the sheet, but it's got to be this version of it that's got the full 4 pi E naught. Substitute your numbers in. For one of the charges, so 4 times 10 to the minus 9, 4 nanocoulombs, divided by 4 pi times E naught's the permittivity of free space on your data sheet, times the distance, 0.12, don't forget to square it. And if you do all of that on your calculator, then you get an electric field strength just due to one of the charges of 2498 newtons per coulomb, and don't round that because we want the combined magnitude of the electric field strength. So, do we need to do a vector diagram here? Could we use Pythagoras? Well, it's a square. So, we could use a right angled triangle. One of the charges is going to have an electric field strength component of 2498. The other one will be exactly the same because the charges are the same at the same distance. So the hypotenuse of that right angled triangle gives us an answer of 3,532. Now, it's a show question. That means we have to round it to 3,500 because that is what we're told in the question. 3.5 times 10 to the 3 newtons per coulomb. Pretty tricky. But a show question always gives you a number, and the reason for that number is so that you can use it in the next part of the question. Part 2, calculate the magnitude of the force acting on this charge. It's a 1.9 nanocoulomb point charge placed at position A in the diagram in the square. Now you might think here, oh man, do we need to do more vectors? No, you don't. We've already got the electric field strength, and therefore, because E equals F over Q, F equals E times Q, where E is your electric field strength. So we can use that from the previous part of the question and simply multiply that 3.5 times 10 to the 3 times the 1.9 times 10 to the minus 9 coulombs. And that will give us the electric force on that charge at position A. Be a very small force, 6.7 times 10 to the minus 6 newtons. And then we're asked for the direction of the force that's acting on this charge. Well, it's a positive charge, and the other two charges are positive as well. So those two 4 nanocoulomb charges are going to repel the 1.9 nanocoulomb charge towards the top of the page. The 1.9 nanocoulomb charge is repelled by the two 4 nanocoulomb charges. And again, if you want to sketch a little right angled triangle just to show the vectors at work, then they will be pushing that charge towards the top of the page. Last wee bit then is 4 marks. It says a fourth charge is now placed at position C on the diagram. That's at the very bottom of the square. So that the resultant force on the charge at position A is 0. What's the magnitude of the charge at position C? Well, we'll need the distance between point A and point C. Sometimes you've got to scroll back quite a long way in a past paper. Let's draw this again. Let's draw this square. Right, so there's our 4 points, A, B, C and D. We want that distance between A and C. Well, we can use Pythagoras again here, because that's a right angled triangle. So 0.12 squared plus 0.12 squared square rooted will give us the diagonal. The diagonal in that square is 0.17 meters. And then if we use our Coulombs Law equation, now we want the resultant force to be 0. So therefore, this charge at the bottom at position C has to have an equal force, an equal but opposite force to the force that's on the charge at position A. Now we know what that force is, because we worked it out in the previous part of the question. There it is. It's 6.7 times 10 to the minus 6 towards the top of the page. So we want an equal and opposite force towards the bottom of the page of 6.7 times 10 to the minus 6 newtons. We're using our shortcut of 9 times 10 to 9 again. We're going to put in our 1.9 nanocoulomb charge that's at position A. And it's Q2 that we're looking for. And we've worked out the distance between A and C at 0.17 meters. So 0.17, don't forget to square it. And then we rearrange for Q2. So Q2 will be equal to 6.7 times 10 to the minus 6 times your 0.17 squared divided by 9 times 10 to the 9 times 1.9 times 10 to the minus 9. We just rearranged that previous line. And that gives us an answer for Q2 of 1.1 times 10 to the minus 8 coulombs. Now it'll be a negative charge, but we're not asked that. We're only asked for the magnitude of the charge, the size of it. So always watch out for that in a question. Watch if it's asking you for the magnitude or the magnitude and direction of the charge. It's only asking us for the magnitude of the charge, so we didn't have to say if it was positive or negative. That's pretty tough. Don't forget, you can use the shortcut. As long as it's not a show question, you can use the shortcut of 9 times 10 to the 9 for the constant in that relationship. There are plenty more past papers for you to have a look at. Usually a question on electric fields every year. So, see you in the next one.